Hello everyone, this is our final presentation on the analysis and redesign of manual coffee grinders. We are Team 20 and our team is listed right here. Manual coffee grinders are used to grind coffee beans into coffee grounds, which can then be used to brew single or multiple servings of coffee using manual brewing techniques like pour over, French press, or stovetop. Our target customers, so we are looking at an estimated production volume of 100,000 units, and our primary target customer is small batch manual brew coffee makers. These are people that don't want to buy coffee from a Starbucks or a store. They don't want to buy grounds that are prepackaged. They want to grind the coffee themselves and brew it themselves in the same day. They want that authentic coffee experience. And then our secondary customer group is hikers and backpackers who might want to brew coffee with them while they're hiking or on trips. This is the assembly CAD before we made our redesign modifications.
This is our fishbone diagram. We started to assemble it from the roller side plate left side and move up gradually until the bean grinder is assembled. And this is our function component mapping matrix. We made some adjustments to it, and we can see that there is some parts that have the same function, so we will try to consolidate it in the next redesign. And we also updated our quad chart classification, as we can see that there is some adjustments made to the each of the group parts. And this is our product family design. Like on the left, we differentiate the fast diagram leaves that is the same or different for each customer group. And on the right side, we differentiate the part that is focused on the platforms or the modules. So the platforms is all the parts that is the product needs, and the modules are the parts that differentiate with the primary or secondary product. And this is the module interface for primary for secondary, where the primary we can adjust the how coarse we want to grind the beans, while the secondary we cannot adjust the coarse of the bean.
Moving into the design for manual assembly portion, in order to select the parts that we would redesign, we looked at the total assembly time for all of the components that made up the assembly. And we noticed that the screws comprise a high contribution of assembly time to the total assembly, and so we wanted a redesign to reduce those. And so for the platform redesign, we went with the rear side plate, front side plate, and roller side plate RS, which is the gear housing for the rollers and the grinders. And then for the modules redesign, we went with the adjustment shaft and adjustment knob. And for the function component mapping matrix, you can see the platform parts that we redesigned all perform the same function of storing the beans, and the module parts that we redesigned all perform the same function of adjusting the fineness. And so before the changes that we made for the gear housing side plates, it was 4 parts, 12 fasteners, and had an assembly time of 110 seconds. And then after the redesign, we were left with 2 parts and 4 fasteners instead of 12, and an assembly time of 36 seconds, so a total assembly time difference of 74 seconds. And the guidelines that we followed were reduce part counts, reduce fasteners, and provide locating features. And the locating feature is labeled as number 3 on the diagram over there. It's an extruded circle to allow for the left plate to be located onto the gear housing plate in order to screw in the screws faster and easier. And for the function of the part, there was no major effect, but for the manufacturing costs, there was some increased cost since the pieces are no longer prismatic extrusions. The shape is a lot more complex now.
For our second design for manual assembly part, we looked at the module of the adjustment shaft and adjustment knob. Before we made the design change, there was 2 parts with 0 fasteners and assembly time of 10.45 seconds. After redesigning it, we condensed this down to 1 part, still 0 fasteners, and assembly time of 4.45 seconds, which was a 6-second improvement. The 3 DFA rules we used were DFA 1, reduce part counts, combining 2 parts into 1. DFA 10, add features for easy insertion. This is the chamfer at the end of the rod for easy insertion at callout number 2. And DFA 8, avoid tangling and nesting. Removing the hole in the adjustment knob removes the possibility of nesting. Overall, this had no major effect on part function, and in terms of manufacturing costs, there was a decrease in material and machining requirements, thus decreasing costs slightly.
For the automated assembly, we selected the subassembly consisting of the drive shaft, the lower shaft, the upper shaft, the coarse roller, the circ roller, and the fine roller, including the clip bearing and the roller side plate left side. We chose the rollers and shafts because they were lightweight parts with high functional importance. And if you look at our function component mapping matrix, they share similar functives indicating that we could consolidate parts. The clip bearing was important because it was high cost and low function. Before redesign, the subassembly consisted of 13 parts, 6 bearings, and a total assembly cost of $11.74. After redesign, we got it down to 7 parts, 3 bearings, and a total assembly cost of $5.30, almost $6.50 less. Looking at our specific modifications, first we reduced part counts by combining the shafts and rollers into 1 piece each, so that instead of having to assemble 6 parts, it was only 3 assemblies. Secondly, we reduced fasteners, in our case bearings, by press fitting into gears on the sides that had gears instead of using bearings because we felt that the bearings were unnecessary and high cost. Third, we reduced part variety by making the teeth on each shaft identical, but more importantly, making the top two shafts the exact same so that you only have two types of different shafts versus three. Finally, we added features to facilitate orientation by adding a notch on the side plate for an assembly machine. Looking at the part function, the lack of variation in teeth size may affect grinding, but we felt that the reward outweighed the risk. And again, the manufacturing cost, it will have less parts, but may increase the cost due to the complex shafts and teeth.
Now on to process selection. We will be looking at the gear housing side plates. The main function of this component is to store beans. Shown below is an engineering diagram of the part. The red arrows denote important features in order to mesh with other points, which is why the tolerance is chosen at 0.013 inches or 0.330 millimeters. Given the material shape, mass, section thickness, tolerance, surface roughness, and economic batch size, we determined that there are three processes that passed all of them. That is die casting, forging, and machining. Of these three, the most economical was die casting. With die casting, we looked at the part and determined that its material cost was going to be 24.5 cents, its operating cost was going to be 44.4 cents, its mold cost was going to be 15 cents, and the overall cost of the part is going to be 83.9 cents. After that, we ran DfM Pro in order to determine some things to fix, giving us a uniform wall thickness problem and a minimum draft angle problem. These two, along with some other design flaws, led us to this redesign. As you can see, we narrowed the walls and made them uniform thickness, avoided draft angles, avoided sharp corners, and avoided side pulls. From there, we cut the cost to 12.5 cents for material cost, 28.6 cents for operator cost, 9.5 cents for mold cost, reducing the overall manufacturing cost by 33.2 cents, or an overall increase of just under 40%. Here is the engineering drawing for this redesign.
For the next process selection, we take a look at the module parts, that is the adjustment shaft and the adjustment knob, and we can see that the main function of the part is to adjust fineness. And when we take a look at the engineering drawing, it is shown that the critical dimensions are the diameters, so like the shaft can fit into the hole properly. So that's how we determine the tolerance. And using the process selection, there is two processes that counts and pass all of them, and we chose machining as the selected process.
Here we have the average cost calculations for our part before the final DfM changes were made to it. These metrics were calculated with the machining process being a CNC lathe for the knob and a mill for the shaft component. From these calculations, we found that the non-productive machining time is 61 seconds, with the productive time being roughly 99 seconds. This led us to find out our total cost per part to be $3.41.
We used the following DFMC guidelines to inform our design for manufacturing. DFMC2 used standard stock. We slightly reduced the dimensions of the piece so that it could be machinable with a 1 5/16 inch diameter stock. DFMC14, add features to facilitate fixturing. We added a flat feature for easier fixturing and removed the draft. DFMC15, minimize tool changes and setups. We did this by removing the unnecessary fillets. In terms of part cost estimation, the analytical method saw a 15.25% reduction in cost. We went from $3.41 down to $2.89. Hubs gave us a 29.17% reduction, going from $2.64 to $1.87. After running this piece back through DfM Pro, we found that all rules were passed when applicable. There was no impact on part function, and in terms of assembly cost, there was a minor decrease in necessary machining, which results in a small reduction in cost.
Now looking at the drawing, we see that the tolerance chosen is 0.005 inches and the critical dimensions are unchanged.
Alongside our redesign, we also provide services that not only benefit the users of our product, but also assist us in reducing our negative environmental impact. The first of these is a recycle refurbish program in which we provide a service for users of our product to return their end-of-life coffee grinders. This provides the customers discounts and benefits on our product, as well as reduces the waste of these parts that would otherwise be discarded. Our second service is a company-provided maintenance, with the cost to the customers being a subscription fee. This provides the customers with the assurance that they can use our product for a long time, while also reducing the waste of our grinders in the case that they break. In conclusion, after our redesign, we were able to reduce the manual assembly time significantly for the housing and slightly on the adjustment shaft plus knob. We also were able to decrease the part numbers in half for the automated section of roller, shaft, and side plates, decreasing the cost by $6.44. Finally, after the implementation of DfM guidelines, improved the manufacturability of both the housing and the adjustment components, leading to save costs of about 33 cents per part for the housing and 52 cents per part for the adjustment shaft and knob. Our design's strongest pros are in its adjustment for assembly, as that is where we saw the most significant reduction following the redesign. However, our design could be further improved if we had conducted a DFA or DfM on other components in our design, such as the housing body or the crank, as these components contain unnecessary material and fasteners. If we were to redo the entire procedure from the start, we would find a model that has a more standard file type, as this file type was more difficult to work with in SolidWorks.